Hi, today we're going to talk about comparing numbers in scientific notation. So now that we've gone back and forth between going to positive scientific notation with positive values of 10 and negative values of 10, so you should be able to write any number in scientific notation, whether it's really large or really small. We're going to talk about how to compare numbers. Okay? So the first thing I want to remind you of is the vocabulary around scientific notation. So scientific notation is a number that's written as the product, so the product right here, of a number and a power of 10. Okay, the number in front is called the coefficient, and the power of 10 is called the order of magnitude. All right, I'm going to refer repeatedly back to this vocabulary during the lesson. All right, so the first thing that we could be asked is, we could look at two numbers in scientific notation, and we could be asked which number is greater. All right, so if we wrote these numbers out in standard form, this 6 times 10 to the 8th power is going to be 6, and since the decimal place is already to the right of the number, I'm going to be adding 8 values of 10, so that's just 8 zeros. Okay, it's always a good habit to go back in and put your commas in so that you can tell the place value that you land on. So that is 600 million, right? Whereas a 5 times 10 to the 9th, well, that's going to be a 5 with 9 zeros. Again, because the decimal place is to the right, anytime I add a power of 10, I'm adding a 0. That's not always the case, but it is with this number. So we have 5, and we can add 1, 2, 3, and actually, since they're in groups of 3, I can put the decimal places already in. Or 9 is a multiple of 3. So this right here is, so this is millions right here, so this is billions. Okay, this is 5 billion and 600 million. So of course this number, we know that 5 billion is more than 600 million. Well, if we look at the powers of 10, we can actually just determine by the powers of 10 which number is greater, and that's why we look at the exponents in this case. So without even looking at the coefficients, the first thing that you're going to do to compare numbers in scientific notation is look at the orders of magnitude. The orders of magnitude tell you the neighborhood that the number is in, right? This tells me that my number is in the neighborhood of the billions because 10 to the 9th power is 1 billion. This tells me it's in the neighborhood of 100 million because 10 to the 8th power is 100 million. So without even having to refer to the coefficient here, I know that something in the neighborhood of a billion is going to be greater than something in the neighborhood of 100 million. So I can use the order of magnitude in order to determine which number is greater. So it turns out that this number is greater. Okay. So another question we could be asked is, we could be given two large numbers, let's say the U.S. population and the world population, and we could be asked how much greater is one than the other, all right? Now, we're going to do this more formally in another lesson where we actually find an exact value, but here we're just going to estimate, all right? So here I'm going to say that the the U.S. population is about 300 million. So that's 3 times 10 to the 8th power, right? We go over 3 spaces, then 6, then 7, and 8. So it's about 3 times 10 to the 8th power. Whereas the world population is around 7 times 10 to the, and that's in the billions, so that's 7 times 10 to the 9th power. Okay, so again, we go 3. I'm going in groups of 3. So this is 3 movements, this is 3, then another 3, so that makes 9. 9 powers of 10 that I've decreased this number by. So we have 3 times 10 to the 8th and 7 times 10 to the 9th. Well, the question of how many times greater is what would you need to multiply the U.S. population by in order to equal the world population. So I'm looking for the factor here that when multiplied by the the U.S. population, I get the world population. So let's think of it this way. Okay, what would I multiply 3 by in order to get to 7? Well, 3 times 2 is 6, so it would probably be, and there's only one, you only have one more number to get there, so it's about 2 1/3. So if I multiply 3 by about 2.3, I would get to 7. Okay, what would you need to multiply 10 to the 8th by in order to get, so what would you need to multiply 10 to the 8th by in order to get to 10 to the 9th? Well, we know our exponent rule, so it's going to be 10 to the first power, because when the product of power says that when you have like bases, you end up adding the exponents. Okay, so here 2.3 times 10 to the first power is what I would multiply the US population by in order to get the world population. Well, let's think about what that number is. 2.3 times 10 to the first power is just 2.3 times 10, but that's just 23. So the world population is 23 times bigger than the US population. All right, and that's just an estimate, but it's a pretty good estimate of how much greater the world population is from the US population. Okay, so what we're doing in this, for this next slide, is we're trying to determine which number is bigger in each of the pairs. Now, I'm giving you different situations here. I'm giving you situations with positive exponents that have different orders of magnitude, that have the same orders of magnitude, and that have a positive order of magnitude and a negative order of magnitude. So in the first one, again, we saw a situation like this on the first slide, where we looked at, this says this is in the neighborhood of 10 to the 8th, and this is the neighborhood of 10 to the 7th. This right here is going to be, let's see, 10 to the 6th is a million, so this is going to be in the neighborhood of 10 millions, and this is going to be in the neighborhood of 100 millions. So this whole thing is going to, anything in the neighborhood of 100 million is going to be bigger than that in the neighborhood of 10 million. Okay, so if they have different orders of magnitude, the order of magnitude that's larger makes the number larger itself. Okay, we don't even need to look at the coefficients. All I have to look at is the order of magnitude. Now, in a situation where the order of magnitude is the same, so these are both in the neighborhood of 10,000s, right? We don't, if they're the same, it's like alphabetical order, right? If they have the same letter, then you move on to the next letter. Well, if they have the same order of magnitude, then we move on to the coefficients. Whatever coefficient's larger in this case is going to be more 10,000. So this is 6.8 10,000s, and this is 2.5 10,000s. So of course 6.8 10,000s is going to be larger. Okay. Now this number right here is, this number is greater than 1. It's actually, this is in the neighborhood of thousands. This is 1.25 thousands, right? So 1,200 and, this is millions. So it's 1,250,000. This right here is very, very small. It's a fraction. So this number is greater than 1 clearly, and this number is less than 1. So we know that this, whenever it has a positive order of magnitude, any number that has a positive order of magnitude is bigger than any number that has a negative order of magnitude. And we do not have to look at the coefficients. The coefficients can be, to sort of X those out here. We do not have to look at the coefficients here. We can just sort of get rid of those as long as we know that the orders of magnitude have two different signs. This one's positive, this one's negative. We automatically know what the answer to these questions are. Okay, so if I ask you to compare numbers, so I've given a bunch of different situations here. Now these are with negative exponents. So which number is greater in each pair? Okay, so in this situation, it's a little bit, so I've given you two orders of magnitude that are different and two of them that are the same. Okay, when the orders of magnitude are different, we don't even have to look at the coefficient. All right. And the negative ones are going to work differently than the positive values, the positive exponent values here. So the more negative this exponent is, the smaller the fraction is that you're multiplying the whole number by, or the coefficient by. So this is actually 10 to the negative 6 power is 1/millionth. Okay, and that's going to be smaller than 1/100,000th. So here, 8 times a small fraction is going to be smaller than 2 times a fraction that's not as small. So here, the number that's bigger in the pair here is going to be this number, because the order of magnitude was negative. Whoops. The order of magnitude was negative, and I want to choose the smallest negative value of the exponent, because then I'm multiplying it by a fraction that's a little bit bigger than another fraction. Both are very small. Let's be honest. Both are pretty small, but 10 to the negative fifth order of magnitude is greater than 10 to the negative sixth. Okay, in this next situation, they both have the same orders of magnitude. So in this situation, we do not refer to the orders of magnitude. We're actually going to refer to the coefficients, and let me show you why. This number right here is going to be, if I move over to the left one, I'd add 4 zeros in order to move to the left 5 times. So we'd have 0.0000134. Whereas this number is the same order of magnitude, so we're going to have 4 zeros and then 285. Well, in this situation, these place values are the same, 1 and 2. So since the 2, they occupy the same place value, and 2 is greater than 1, we know that this number is actually bigger than this number, okay? Now, so if they have the same orders of magnitude, whichever has the greatest coefficient is the bigger number. Okay, let's deal with some more how many times greater problems. So if we have two numbers here that have that use positive or negative values of the negative powers of 10 in order to express them in scientific notation, let's try to compare them. So the size of a comma in a 12-point font is about 0.0006 meters long. And the size of a bacteria cell, like the one you see pictured here, is 0.000021 meters in diameter. How many times greater is the comma than the bacteria cell? Well, the comma can be written as 6 times 10 to the, let's see, negative 4, because we move in 1, 2, 3, 4. And the bacteria cell's diameter can be written as 2 times 10 to the 1, 2, 3, 4, 5, negative 6. Okay, so the question is, what would I need to multiply the bacteria cell by in order to get up to the comma cell? So let's look at the coefficient here first. So 2 times 3 would get us up to around 6. And 10 to the negative 6 times some power of 10 is going to be equal to 10 to the negative 4. So think about what would you add to negative 6 in order to get to negative 4. The answer here would be 2. So it's 10 squared. So the coefficient you need to multiply by 3 in order to get from one to the other. This one you need to multiply by 10 squared. Well, we put those two ideas together, 3 times 10 squared, that's going to be 300. Okay, so the size of a comma in 12-point font is 300 times bigger than the bacteria cell's diameter. Finally, the last problem here is, let's say that numbers are neither, sometimes when you have an operation, you get numbers that are neither in scientific notation nor are they in standard notation. So for instance, this first number is not in scientific notation because the coefficient's not between 1 and 10. So what do we do in this situation? Well, the coefficient's too large. We need to make it smaller. So I'm going to go to the left by 2 spaces, okay? So I'm going to rewrite the coefficient as 3.6589. Now, when I do that, I'm making this number smaller. Anytime I make the coefficient smaller, I'm going to add values. Essentially, I'm taking powers of 10 away from the coefficient. So I need to add those values, those powers of 10 onto the exponent of the 10. So here I took 2 powers of 10 away from the coefficient, and I need to add those powers of 10 into the exponent to make these numbers equal to each other, right? They are equal in value, this number up top that we started with and the number that's actually in scientific notation. So what I want you to understand is that when you make the coefficient smaller, you make the exponent larger and vice versa. Okay, they work inversely to each other. Meaning as one gets larger, the other one gets smaller, or as one gets smaller, the other one gets larger. The coefficient and the order of magnitude work inversely with each other. Likewise, this number is too small. This coefficient is between 0 and 1, not 1 and 10. So I want to borrow some powers of 10 here. Okay, so I want to borrow 1, 2, 3 powers of 10. So I'm going to the right by 3, and I need to subtract those powers of 10 from the exponent here. So I'm going to write that as 7.52 times 10 to the first power. Now this number is in scientific notation because the coefficient is between 1 and 10. and it's multiplied by a power of 10. Okay, so let's try it when the coefficient's too large and you have a negative exponent. Here I want to go to the left by 1, so it means I want to add a power of 10 into this part of the scientific notation. So 1.236 times 10 to the negative 6. That's how you write that number in scientific notation. And here the coefficient's too small, so again I want to borrow powers of 10, so I want to borrow 1, 2, 3 powers of 10, so I go right by 3. So I need to take away those powers of 10 from the this part of the number. So I have 7.52 times 10, and then negative 3 minus 2, if I use keep change, it's negative 3 plus negative 2, so this has got to be negative 5. Okay? And that's the end of the lesson for today. Thanks.